So back in Calc 1, we actually talked about two different kinds of extrema. If you had a function y equals f of x, you might have a function who, say, looked like this. Now, a function of this particular form would have local extrema. For example, this function would have two different local maximums, one right here and one right here, corresponding to these particular x values. This function also has a single local minimum, corresponding to this particular x value here. The idea was that local extrema represented bends in a graph. However, there was a second kind of extremum out there, what was known as a global or absolute extremum. And the idea of a global extremum was that we would take all of the different y values and we would find the highest y value that there ever was, and we would call this the global or the absolute maximum. And we would look through and take all of the different y values and we would find the one lowest y value, and this would be called the global minimum. And so the global maximum will occur at some x value, and a global minimum might occur at some other x value right here. And so that was a competing idea. Said differently, global extrema represented the largest and or the smallest output values that were attainable, period. They had nothing necessarily to do with the shape of a graph. So in some cases, a global maximum might be the same thing as a local maximum. The graph might bend at that point, and that's the highest point attainable. However, there's no reason that a local maximum has to be a global maximum, or that a local minimum has to be a global minimum. And in fact, a global extremum, like this local or global minimum down here, doesn't have to be a local extremum. It doesn't have to be a bend on the graph. It might actually physically be an endpoint. Now, one of the things that you might remember in Calc 1 is that most functions don't have global extrema. If you were to sort of pick some random function, say this cubic right here, it might have local extrema, here's a maximum and here's a minimum, but it doesn't have a global maximum because the function keeps going up and up and up. There's no highest y value it reaches. It also has no global minimum, no lowest value that it reaches. So a function doesn't have to have a global maximum or a global minimum. However, if we were to take this function and look at it on a specific domain, imagine only looking at it from this x value over to, say, this x value here. So we'll only focus on the part of the graph that lives above this chunk. In that case, we would be focusing our attention on just this portion of the graph. And so we could ignore the rest of it and just see this bit right here. Now notice that on this bit, by getting rid of the escaping graph on the top, we've actually built a global maximum. And by preventing the graph from running down, we've also found a global minimum. In this case, these kinds of extrema are known as constrained extrema. Constrained extrema refer to the largest and smallest outputs that are attainable over a restricted or constrained domain of the function. One last little piece of language from Calc 1. It's the actual output values that are referred to as the global maximum and the global minimum. The input values are where they occur at. So if, for example, we were to include some tick marks on this graph, then we would say that this function has a global maximum of 4, since the output value is 4, and it occurs at x equals 5. On the other hand, this function would have a global minimum of negative 1.5, and it would occur at the value x equals 2. These ideas can be generalized immediately to functions of two variables. Imagine we had a function of two variables, say x squared plus y squared, which is the paraboloid, the cup that opens along the z-axis. We've seen before that this particular cup has a single local minimum at the origin. but no local maxima. However, we've also graphed this cup, and we know that the entire graph lives above the plane z equals 0. It touches the xy plane at z equals 0 and then spends its whole time getting higher and higher than that, which tells me that this particular minimum is not just a local minimum, but it's also a global minimum. It is the lowest output value we can get on this particular function. However, this function has no global maxima because the parabola just goes up and up and up. So there's no highest output value. We can always get a higher and higher z value by drawing a larger and larger version of this paraboloid. On the other hand, last time we looked at the function z equals 3y squared minus 2y cubed minus 3x squared plus 6xy. And we used maple to render its graph, and it looked something like this. This particular function had a local maximum at the point 2, 2. And it had a second critical point, which was a saddle right at the origin. But this particular function doesn't have a global maximum because this portion of the graph could be extended vertically as high as we wanted, and it didn't have a global minimum because this portion of the graph could be extended down as low as we want. So this is an example of a function who had local extrema, but not global extrema. A sort of more extreme example of this would be to take any plane, z equals, say, ax plus by plus c. So imagine that you had some sort of a plane, like this plane right here. Well, planes have absolutely no local extrema whatsoever, but they also have no global extrema, because we'll just take the plane and figure out which direction it's pointing up, and then if you keep following in this direction, the z values will always increase, whereas if you walk in the other direction, the z values will always decrease. So this would be an example of a function who wouldn't have local or global extrema. However, if you were to go down into the plane, and rather than look at this function over the entire xy plane, imagine instead looking only over, say, this section of it right here. So for every point in this, we'll go and we'll find its corresponding y value or z value. So this point would go right here. This point, say, might go right here. This point might go right here. This point might go right here. And then all of the interior points would go inside here. And so what we'd have is if we focused only on this constrained portion of the graph, we would have not an entire plane, but just some small chunk of plane. And clearly this small chunk of plane has to have some sort of a maximum. If this was the highest corner right here, then this particular point, whose z value might mark up right here, would become a constrained maximum. Whereas this point on the opposite corner, who might correspond to, say, this particular value on the z-axis, would become a constrained minimum. So these concepts from Calc 1 carry on over into the two-variable setting. Let's find the global extrema of the function f of xy equals x squared plus y squared minus 6x minus 2y plus 1. In this case, we're looking for the largest and smallest values of this function at all. But since it's global, it means we have no restrictions on the function. So any global extrema would have to be a local extrema at the same time. And so really all we need to do for this case is let's just hunt for the local extrema first. That was what we did last time. So the local extrema, that's going to occur when the gradient of f is either 0 or undefined, doesn't exist. So let's compute the gradient of f quickly. The gradient of f in this case would be 2x minus 6. The second component would be 2y minus 2. Notice that since these are both polynomials in x and y, they are always defined, so there's no place where the gradient doesn't exist. On the other hand, if we set the two components equal to 0 and solve these two equations and two unknowns simultaneously, the first equation will get us x is equal to 3, the second equation will get us y is equal to 1, and so that means, putting the two solutions together, that the point 3, 1 is the only critical point. At this point, we know that this is the one and only place where an extremum can occur, but we don't know what kind of an extremum it is yet, so we could go and use the second derivative test to classify it. Remember, the second derivative test says we want to go and take the determinant of the matrix whose components are fxx, fxy, fyx, and fyy. So let's work out those entries. If this is the derivative of f with respect to x, then its derivative fxx would be 2 and fxy would be 0. Since this is derivative with respect to y, its derivative with respect to x would be 0, and its derivative with respect to y would be 2. And so the determinant of this is 4. Since that's greater than 0, we know that we're at an extremum. And since the fxx term is positive, this tells us that we have a local minimum. Now, all of that information is great, except it still doesn't tell me whether or not this is a global minimum. Is this the lowest point that we could attain right here? Unfortunately, there's no fast and dirty way of detecting whether or not something is a global extremum. The best thing that we can do is graph something like this using our graphing techniques, or having Maple go and do it. So let's go and take a look at what a graph might be. This was something that was shaped vaguely like a paraboloid, but it was a paraboloid whose vertex occurred at the point x equals 3, y equals 1, and then apparently z equals minus 9. And so, since it's an upwards opening parabola, that tells me that this local minimum is also a global minimum. And so we have a global minimum at the point 3, 1, and a global minimum value of minus 9, because that's the z-value I get when we plug in the point 3, 1. Well, let's take a variation of this particular problem. Rather than look at the global extrema of this function, let's instead look at a constrained extrema problem. Let's find the extrema of the same function, x squared plus y squared minus 6x minus 2y plus 1. But now let's have it subject to a constraint in the domain. The constraint x plus y always needs to be 2. So a different way of looking at what we have just done here is that we had this function. And rather than try to draw a three-dimensional version of it, I'm going to draw a contour plot. So we knew that it was an upwards opening parabola. We saw that it had a minimum right here at x equals 3, y equals 1. And then because it was a paraboloid, each one of its level sets were sort of these round shapes. So I'll put a little marker to myself that this was the lowest level set, and that the level sets are increasing in this direction. Now this is based on my ability to use every point in the plane to figure out what's going on. Now we want to focus our attention on a constraint. Instead of looking at every point in the xy plane, we only want to look at those points where x plus y is equal to 2. Now, that's the equation of a line. If x is equal to 0, then y is equal to 2. If y is equal to 0, then x is equal to 2. And so that right there would be the equation of this particular line right here. And so the idea of the constrained extrema is we would like to find the highest or the lowest point of the function on this particular curve right here. How do we find the extrema of the equation z equals x squared plus y squared minus 6x minus 2y plus 1 subject to the condition that x plus y is equal to 2? We can't go and use this approach anymore, because this approach involves us looking over the entire domain, and we're sort of emphatically not looking over the entire domain. The one and only critical point, 0, doesn't happen to, 3, 1, doesn't happen to live on this curve at all. And so this approach isn't going to find me what I'm looking for. However, we only want to look at the corresponding y values to points on this particular curve right here. Well, we could actually work out what those output values, those z values are, if we could solve this equation for one of the variables and plug it into this top equation. But that's easy to do. This equation is just y is equal to 2 minus x. And so if we were to plug this in, we would get that z is equal to x squared plus y, which is 2 minus x quantity squared, minus 6 times x minus 2 times y, which is 2 minus x plus 1. Now if we clean up this expression, we're going to have x squared plus 4 minus 4x plus x squared minus 6x minus 4 minus 2x plus 1. So if we collect the x squareds, we're going to have 2x squared. If we collect negative 4x minus 6x plus 2x, that will get us minus 8x. And if we take 4 minus 4 plus 1, we'll get 1. And so now we have a formula that tells me the output values as long as I can give you an input value in x. Notice that this is now z in terms of x only. Since we're looking to find the extreme values of z, we can go and use Calc 1 techniques. And the first thing to do in Calc 1 is to take the derivative of this with respect to x and see what we get. Well, the derivative of this with respect to x would be 4x minus 8. Whenever the derivative is 0, we're at critical points. So if we set this thing equal to 0, we would get 4x is equal to 8, or x is equal to 2. And so that tells me that the only place where this particular formula right here ever takes on an extreme value as a function of one variable is when x is equal to 2. Now that I know that x is equal to 2, I can use the constraint to figure out what the corresponding y value is, and that would be 0. So we find out that the only candidate is the point 2, 0. Over here in my picture, that would be this point right here. But this is only a candidate. It doesn't tell me whether or not I'm at a maximum or a minimum. I can't go and use the second derivative test because this wasn't a critical point of the original function. So how do we tell whether or not this is a max or a minimum or anything else? Well, one useful piece of information we've already got written for us, this graph. Let's just take a look at what happens right here. We know that the middle is the lowest level set. So then as I draw more and more level sets, this is a small z value, a slightly larger z value, a slightly larger z value, a slightly larger z value. So at the point 2, 0, I'm hitting a level set which is actually fairly close to the point 3, 1, which means that this is a pretty low level set. It's got a low z value. Every other point on this curve corresponds to one of the bigger level sets. So the point 2, 0 corresponds to a small level set. All of the other ones correspond to larger level sets. That tells me that this guy right here has to be a constrained minimum. So now we can answer the question. We have a constrained minimum value at the point 2, 0. And it's a minimum value of, well, let's plug in 2, 0 into here. And so that value would be negative 7. So we have a minimum value of negative 7. It occurs at the point 2, 0. Notice that this value is larger than negative 9, which we knew was the global minimum value. So that kind of at least is consistent right here. It turns out, however, that the work we did in this particular example, and especially the argument based on this picture, can be used for all kinds of problems. And so let's focus on this right now. Let's suppose you had some function f of xy. Now I'm going to graph it, but I'm not going to graph it three-dimensionally. I'm simply going to go and graph its contour plot. So let's say that its lowest contour is right here. Z equals, let's just say, the lowest contour plot. The lowest contour. And then maybe the next contour is this one right here. And then the next contour is this one right here. And so on, up into the highest z value. So we have a contour plot. Now let's imagine that we had some kind of a constraint curve, like this one. So my question would be, where are the constrained extrema of the function f on this particular curve right here? For example, would this point right here be a constrained maximum or minimum? The answer would be no. I know whatever this z-value is right here, this point would have a higher z-value because it's on a higher level set. So it couldn't possibly be a maximum. It also couldn't be a minimum because I know that this point right here, which is on a lower level set on the curve, would have a smaller z-value. So it couldn't be a minimum. Pretty much I can make that argument at almost any point you pick. Draw a random point, say this dot right here. Ask, is it a max or minimum? Well, it can't be a maximum because if I were to go to this point right here, I'd have a higher z-value. And it can't be a minimum because this point right here has a lower z-value. So how could we find a minimum? Well, one of the things we could do is we could look for the lowest level set we've plotted, this one. But this particular level set doesn't contact the curve at all, which tells me that no point on the constraint curve ever hits this lowest z-value. The next lowest z-value I plotted was this one right here, which hits the curve at 2 different spots. Would this be the lowest value that we can hit on the curve? Well, probably not, because I could draw maybe an even more shallow level set right here. And since this level set is going downwards, it would have a lower z-value. And so I could actually keep doing this. I could keep bringing the lowest level set up, the lowest level set that doesn't hit the curve up, and the lowest level set who hits the curve down, and sooner or later I will find one particular level set who just grazes the constraint curve. So let me focus on that one guy right there. This particular one is the lowest level set who makes contact with the curve right here. And you'll notice that this level set appears to be tangent to the surface. If we were to make it go any lower, it wouldn't contact the surface at all. But if we were to bring it up any higher, it would contact the surface in at least 2 different spots. And that would give me higher values right here. Well, let's go and do the same thing on the maximum size of things. This particular highest level set that I plotted never gets anywhere near the curve, so I can never get this high. Same thing is true for this particular level set. However, the third highest level set we drew contacts the curve in 2 different places. That means there's 2 different points who have this particular output value. But if I were to draw a curve who somehow splits the difference between these 2 guys, say this curve right here, then points on this curve would be a little bit higher than points on the yellow curve. Would they be the largest value we could get? Well, we could do the same thing. We could keep plotting level curves until we get to one particular level curve who just grazes the surface at a specific point. If we focus our attention on this one point right here, we know that we can't go any higher because a higher level set would simply not contact the constraint curve. And so once again, we see that at this highest point right here, the level set of f is tangent to the constraint. And so we have a decent answer to this question. Where are the constrained extrema of f on this curve? Well, they occur at the points where the level sets of f are tangent to the constraint curve. Of course, if you think back to our discussion of gradients, if we were to plot the gradient of the function f, then the gradient is always level or always normal to a level set and points in the direction of increasing z-values. In particular, notice that this means that the gradient at these 2 points, the maximum point and the minimum point, has to be at right angles, has to be normal to the surface. We can rephrase this statement as follows. Rather than saying the level sets are tangent to the constraint curve, we could say that the constrained extrema occur at the points where the gradient of f is normal to the constraint curve. But I have one last trick up my sleeve. Remember that every curve in the xy plane can be expressed as the level set of some function, which we'll call in this case g of xy. Now this particular function will have its own gradient, a gradient who points normal to this particular level set at every point. So we have this blue gradient who's always normal to the level set. At the maximum and the minimum points, that means we have two different vectors who are normal to this level set. The gradient of g, who's normal to the level set by properties of gradients, and the gradient of f, who's normal to the level or to the constraint curve, which is the level set of g, by the fact that it was at the extreme level sets of f. What this means is that these two gradients, the gradient of f and the gradient of g, at the extrema on the curve, they need to be parallel because they're both normal to the curve right here. And so we can summarize this as follows. If f of xy is subject to the constraint g of xy equals c, some curve, then the extreme values of f over the constraint can only occur at those points where the gradient of f is parallel to the gradient of g. Now you might remember that the only way vectors are ever parallel is if one vector is a multiple of the other. So I could rewrite this bottom equation by saying that the gradient of f and the gradient of g are scalar multiples of each other, and the tradition is to let the scalar multiple be called lambda. This is sometimes called the Lagrange multiplier theorem. And it gives us a fairly effective way for finding the locations of extrema on constraints. The method is as follows. To find a candidate for the extrema, all we need to do is solve the following system of equations. We have to first solve the gradient of f is equal to lambda times the gradient of g, but we also need to make sure that we find a value of xy that plugs into g to make it equal to c, otherwise we're not on the constrained curve at all. And so the system of equations we need to solve are the gradient of f is equal to lambda times the gradient of g, and g is equal to c. This is actually three equations in three unknowns. It doesn't look like it the way I have it written down here, but we can see that in an example. So let's go back and revisit the second example we looked at. Find the extrema of the function f of xy equals x squared plus y squared minus 6x minus 2y plus 1, subject to the constraint curve y plus 1 equals 2. X plus y equals 2. We showed using an ad hoc approach that the constrained minimum occurred at the point 2, 0, and that the value was negative 7. Let's see if we can recreate this result using the method of Lagrange multipliers. So to use the method of Lagrange multipliers, we need to solve a system of equations. The gradient of f is equal to lambda times the gradient of g, and g equals a constant. Now f is the function that we're attempting to find the maximums and minimums for, so I can work out the gradient of f, no problem. That would be, let's see, 2x minus 6 for the first component, and 2y minus 2 for the second component. But what about g in this? Well, g is simply the constraint equation. Now notice that our constraint equation is x plus y equals 2. If we were to set g of xy to be the left-hand side of this, x plus y, then we see that our constraint is nothing more than the equation g of xy is equal to 2. It's the level set of the function x plus y. So we can take the gradient of g, this particular function, and come up with 1, 1. And so our equations are going to be the gradient of f, 2x minus 6, comma 2y minus 2, is equal to lambda times the vector 1, 1. And the second equation is g equals c. That's the constraint equation, x plus y equals 2. Now remember how I said that this is really three equations and three unknowns? Well, that's because the top involves components. So if we were to write out what these components are, we're going to have, let's see, the x component would be 2x minus 6 is equal to lambda times the x component on the right-hand side, which is 1. We'll take the y component on the left-hand side, that's 2y minus 2, and that should equal lambda times the y component on the right-hand side, which is 1. And then we have the constraint equation x plus y equals 2. Three equations in three unknowns, x, y, and lambda. So how do you solve three equations and three unknowns? Well, the same way you solve any number of equations and unknowns. Solve one of the equations for one variable, plug it in, solve the next for the next variable, plug it in. So let's do that. If we take the top equation and solve it for lambda, we get lambda is equal to 2x minus 6. I'll then plug that into the second equation. The second equation now reads 2y minus 2 is equal to lambda, but lambda is 2x minus 6. So that means that we're going to get 2y is equal to 2x minus 4, or y is equal to x minus 2. Now that I have y, I can plug it into the third equation and get x plus y, which is x minus 2, is equal to 2. So that gets me 2x minus 2 is equal to 2. That's 2x is equal to 4, and so x is equal to 2. And so now I have a solution to this system of equations. Our solution is x is equal to 2, y is equal to x minus 2, 2 minus 2 is 0, and lambda is equal to 2x minus 6. So that would be 4 minus 6, or negative 2. So we have a solution to these three equations and three unknowns. The x and the y values are the point we're looking for, and so we found out that the only extremum could possibly occur at the point 2, 0, and we're right back where we were before. Now, it doesn't actually tell me whether it's a maximum or a minimum. All it tells me is that this is the location. I'd still have to go through the same graphing argument we did before. Let's try a slightly more complicated constraint curve, but let's just keep this function with us right now. Let's find the extrema of this function on the new constraint curve x minus 1 squared plus y minus 1 squared equals 1. So before we do the Lagrange multiplier method, let me at least try to go and again draw the picture that corresponds to it. We've already seen that the level sets of the function f are concentric circles centered at the point 3, 1. So they're circles that radiate outwards like this, and the bigger the circle, the bigger the z value. On the other hand, our constraint curve is this right here. Now remember that x squared plus y squared is a circle of radius 1. By replacing x with x minus 1 and y by y minus 1, we've simply moved the graph 1 unit to the left, or sorry, 1 unit to the right and 1 unit up. So this would be a circle centered at the point 1, 1 of radius 1. And so that would be our constraint curve. Now sort of notice that there's two places on the gray constraint curve that are tangent to level sets of the function. This farthest point right here, and then this other sort of extreme edge right here. So these would be places where the gradient vectors to the gray circle and the gradient vectors to the green level sets would both be parallel. And so based on this picture, I'm getting the impression that this farthest most left point is going to be the maximum, and this farthest rightmost point is going to be the minimum. Now let's see if the Lagrange multipliers method backs that assessment up. So we're going to need to solve the equations gradient of f is equal to lambda times the gradient of g, and also g equals c, where g equals c is the constraint equation. So let's see. Our function f is given right here, so the gradient of f is going to be 2x minus 6 and 2y minus 2, just like it was before. On the other hand, our constraint equation, this expression right here, takes the form of a function g of xy equals a constant. So it's a level set of a particular function. The function is x minus 1 quantity squared, y minus 1 quantity squared. So that would mean that the gradient of this function g is just going to be the derivative of this expression right here. So if we differentiate with respect to x, we're going to get 2 times x minus 1. If we differentiate it with respect to y, we're going to get 2 times y minus 1. And if I clean that up, that's just going to be 2x minus 2 and 2y minus 2. What would be our Lagrange multiplier equations? Well, they're going to be the gradient of f equals lambda times the gradient of g. That means that the x component of the gradient of f, 2x minus 6, had better be lambda times the x component of the gradient of g, 2x minus 2. It also means that the y component, 2y minus 2, had better be lambda times the y component of the gradient of g. And then the last equation is simply the constraint curve, x minus 1 squared plus y minus 1 squared is equal to 1. So let's go through and solve this particular system of equations. So the first thing I'm going to do is I'm going to pick one of these equations and solve it for one of the variables. And this equation seems suspiciously easy. Just check it out. It says that lambda is equal to 2y minus 2 over 2y minus 2. Well, that would mean that lambda is equal to 1. So now that I know the lambda value, I could plug that into the top equation. So if I do that, I'm going to get 2x minus 6 is equal to 1 times 2x minus 2. So 2x minus 6 is equal to 2x minus 2, which means that negative 6 is equal to negative 2, which means crap, something has gone wrong right here. I can't solve these three equations. Negative 6 is not equal to negative 2. What went wrong? Well, what went wrong was this part right here. This is true provided that y is not equal to 1. On the other hand, if y was equal to 1, then the second equation would be satisfied already, because the second equation boils down to 0 equals lambda times 0. So y equals 1 is a second solution to the second equation. The second equation just had two different solutions, x equals 1 or y equals 1. Now if I take y equals 1 and plug it into the bottom equation, we're going to get x minus 1 quantity squared plus y minus 1, which is just 0 squared, equals 1. That means x minus 1 quantity squared is equal to 1. If we take the square roots on both sides, x minus 1 is equal to plus or minus the square root of 1, which is 1, or x is equal to plus or minus 1 plus 1. So x is either equal to 1 plus 1 or minus 1 plus 1. And so we get two different values for x. Finally, we need to go and plug those values into the top to see if we can find lambda. So if x is equal to 2, then this equation becomes 2 times x minus 6 is equal to lambda times 2 times x minus 2. So that gets me negative 2 is equal to lambda times negative 2, positive 2, sorry, and that means that lambda is equal to 1. So we found a solution. X equals 2, y equals 1, and lambda equals 1. On the other hand, if x is equal to 0, then this equation becomes negative 6 is equal to lambda times negative 2, and that means that lambda is equal to positive 3. And so we found another solution. X equals 2, x equals 0, y equals 1, and lambda equals 3. Every solution to this system of equations corresponds to a critical point, or a potential, extremum. This one gives me the extremum value of 2, 1. This one gives me the extremum value of 0, 1. And if we actually pay attention to our graph, the point 0, 1 is the left endpoint, and the point 2, 1 was the right endpoint. And so this is consistent with our graph. This means that we have a constrained minimum at the point 2, 1, because that's the point who's on the smallest level set, and a constrained maximum at the point 0, 1, because that's the point on the largest level set. What are those values? Well, the minimum value is simply going to be f of 2, 1. So that would be negative 8. Whereas the maximum value will simply be f evaluated at the point 0, 1, which is 0. And so we have this problem solved. Now we can summarize the attack we used in the previous problems fairly efficiently as follows. The method of Lagrange multipliers. Given a constrained optimization problem that takes the form find the maximum or the minimum of some function f of x subject to the constraint that g of x is equal to c, where x in this case is the variable point xy, then the only possible values of x that solve this problem must also satisfy the equations the gradient of f at x is equal to lambda times the gradient of g at x, and g at x is equal to c, for some scalar value lambda, which is called the Lagrange multiplier for this problem. Now, although we verified this sort of intuitively in the case of two variables, it's worth pointing out that this restriction right here isn't necessary. In fact, this result is perfectly valid for functions of 3 variables as well. Let's take a look at an example. Find the point on the plane 2x plus y minus z equals 5 that's closest to the origin. So, as usual, let me try to draw some cheesy picture of what's going on here. We've got this plane floating around in space. And then we have the origin. And I can tell that the origin is not on this plane because if I plug in 0, 0, 0, I get 0 and not 5. So what we want to do is we want to take every point in the plane and measure the distance to the origin. And we'd like to find what point in this plane is the closest to it. If we were to isolate one of these particular points as the point x, and then this is the origin right here, then the distance from the point x to the origin would be nothing more than the length of the vector OX. So that would be the length of the vector x, y, z, or the square root of x squared plus y squared plus z squared. So we could call this, say, d for the distance. So what do we want to go and do? We would like to minimize the distance of a point to the origin subject to the point x staying on that plane right there. In other words, we'd like to minimize the square root of x squared plus y squared plus z squared subject to the constraint that 2x plus y minus z is equal to 5. And so in this case, we've identified an objective function, something that we're trying to maximize or minimize, and we've identified the constraint equation and the corresponding level set. So this is the guy who's going to be playing the role of f. This is the guy who's going to be playing the role of g. So let's set up the Lagrange multiplier problem and solve it. And so our Lagrange multiplier setup is f is equal to x squared plus y squared plus z squared quantity square root. G is equal to 2x plus y minus z. And we want to solve the gradient of f is lambda times the gradient of g, and g is equal to 5. So let's work out what these things are first. For the gradient of f, the first component is going to be the derivative of f with respect to x. So using the chain rule, we'll have the derivative of blank to the 1/2 power is 1/2 blank to the negative 1/2 power times the derivative of the inside, the derivative of blank, which would be 2x. And so if we were to clean this expression up, these would cancel, and so we're just going to have x divided by x squared plus y squared plus z squared to the 1/2 power. Now, since the equation is completely symmetric in y and z, we should get the exact same things, or corresponding things, for the derivatives in y and in z. On the other hand, the gradient of g is going to be much simpler. It's just going to be 2, 1, minus 1. And so our Lagrange multiplier equations, well, notice that this first equation is really a statement about 3 components. So it says that the x component of f and the x component of g should differ by a constant. So our first equation will be x divided by x squared plus y squared plus z squared to the 1/2 power is equal to lambda times 2. The second equation should scale by the same, so our second equation will be y over x squared plus y squared plus z squared to the 1/2 power is equal to lambda times the other coordinate 1. And then the third coordinates should match up, so we'll have z over x squared plus y squared plus z squared to the 1/2 power is equal to lambda times negative 1. And then finally we have the constraint. 2x plus y minus z is equal to 5. So, 3 equations in 3 unknowns. Well, let's see what damage we can do with this. Notice that the middle equation actually solves us for lambda directly. So we can plug this into the other equations. So if we plug this into the equation on the left, we're going to get that x over x squared plus y squared plus z squared to the 1/2 power is equal to 2 times lambda, which is y over x squared plus y squared plus z squared to the 1/2 power. Notice that we could multiply both sides by this expression, and so what we're going to be left with is x is equal to 2y. If we take this formula for y and plug it into the expression for z, a similar argument is going to get us that z is equal to negative y. Finally, we can take these 2 equations for x and z and plug them into our constraint. We're going to get 2 times x, which is 2y, plus y, minus z, which is negative y, is equal to 5. So that's going to get us 4y plus y is equal to 5. That's 6y is equal to 5, so y is equal to 5/6. Now that we have the value for y, we can go backwards and figure out that z has to be negative 5/6. Now that we also have the value for y, we can figure out that x has to be 10/6. And last but not least, we can plug in all of these values into any one of our equations to work out the corresponding value of lambda. And so we found that there's one and only one solution to this system of equations, and that solution is x is equal to 10/6, y is equal to 5/6, z is equal to negative 5/6, and lambda is equal to 1 over root 6. And so that means that the only point in question is this point right here. So the point 10/6, there's 3/5, comma 5/6, comma minus 5/6 is the only candidate. Now, is it a maximum or a minimum? Well, in this case, I'm just going to go and appeal to common sense right here. I've got a plane, I've got a point, the origin. As I move farther and farther out on this plane, points are going to get farther and farther and farther away from the origin. So it makes sense that there's no such thing as a maximum distance you can get from the origin. However, if I get close enough, it does make sense that I should have a minimum. So based on common sense, this must be the point that minimizes the distance. In other words, this is the closest point to the origin on the plane. Now, one of the problems we've been having is that Lagrange multipliers is great for finding extrema, but it's not so great for testing them. In order to give a useful tool for finding these extreme values, we'd like to talk about one more type of constraint region. A constraint region is a subset of the plane that consists of possibly several curves, together possibly with the points inside these boundary curves. So for example, the region that I've drawn over here, which sort of consists of 4 different curves, C1, C2, C3, C4, would be an example of a constraint region. If we also included all of the points inside this shape, that would be another example of a constraint region. Now, why do we care about constrained regions? Well, the main reason is this important theorem. And that result is called the Extreme Value Theorem. It says, given a constraint region R, if 1, R is bounded, and all R being bounded means is that it's sort of finite in scope, that it has a finite area, that it doesn't run off to infinity on any side. And if f is continuous on this region, then f always has a constrained maximum and a constrained minimum on that region. In fact, the extrema can only occur at one of 3 places. 1, they can occur somewhere inside the region, and then only at a place where the gradient is equal to 0. 2, on one of the various boundary curves at a point that satisfies the Lagrange multiplier problem, or 3, at one of the intersection points of 2 of the different curves. Now, this sounds like a heck of a lot of places for it to happen, but the upshot is this. Make a list of these points, the places inside the region where the gradient is 0, the places on the curve that satisfy the Lagrange multipliers problem, and the points who are the intersection of any 2 of these curves. And plug these points into the function f of xy. The biggest value is guaranteed to be the maximum, and the smallest value is guaranteed to be the minimum. Let's take a look at an example. Let's find the maximum and minimum values of the function f of xy equals 3x plus 4y over the circle x squared plus y squared equals 25. So in this case, we have but one constraint. It's just a circle of radius 5. Right, this equation right here. Notice that this would be a constrained region because it consists of a single curve, and this constrained region is bounded. It's not going off to infinity, and last but not least, this particular function, being a plane, is continuous on it. So the extreme value theorem says it's got to have a maximum or a minimum. In fact, it goes one better. Since there's only one boundary curve right here, it says that both values have to lie on this curve, since there aren't any points of intersection and there's no interior. And so all we need to do is find all of the different critical points on the circle, figure out which one has the biggest z value and which one has the smallest z value, and we're done. So let's go and solve one round of Lagrange multipliers. So our function is going to be the function 3x plus 4y. Our constraint function is going to be x squared plus y squared. And our Lagrange multiplier setup will be the gradient of f is equal to lambda times the gradient of g, and in this case g is equal to 25. So if we work out the gradient of f, we're going to get 3, 4. If we work out the gradient of g, we're going to get 2x, 2y. And so our 3 equations and 3 unknowns are going to be 3 equals lambda times 2x, 4 equals lambda times 2y, and x squared plus y squared is equal to 25. Now, if we solve this first equation for lambda, we're going to get lambda is equal to 3 divided by 2 over x. We can then plug that into the second equation to get 4 is equal to lambda, which is 3 over 2x, times 2y, or y is equal to 8/6 or 4/3 x. So now we've got the y value, we can plug that into the constraint. Into the constraint equation, we're going to get x squared plus y, which is 4/3 x squared, is equal to 25. We get x squared is equal to 9, and so x is equal to plus or minus 3. Now that we know the x values, we can find the corresponding y values, and then we can go back and find the corresponding values of lambda. And so we found two solutions to the system of equations. Since we've got complete solutions, then these will be our corresponding points. And so we found that the only 2 points on the constraint circle are going to be 3, 4, and -3, -4. These are the only candidates that we could have for maxes and mins. Now if we work out what f of 3, 4 is, that's going to be 3 times 3 plus 4 times 4, which is 25. If we work out f of -3, -4, we're going to have -3 times 3 plus 4 times -4, which is -25. Clearly this number is larger than that number, and so that tells me that we have a maximum value of 25 at the point 3, 4, and we have a minimum value of -25 at the point -3, -4. Isn't that much nicer than having to go and graph or plot contours? Let's take a look at one final example. Find the maximum and minimum values of the function f of xy equals 2 plus 2x plus 2y minus x squared minus y squared over the triangular region with vertices at the points 0, 0, 9, 0, and 0, 9. So let me take a look at what this region is right here. We've got 3 vertices, 0, 0, 0, 9, and 9, 0. And so we're looking at this triangular region right here. And since it's a triangular region, it means I'm looking at all of the points on the inside of it as well. So first off, notice that this region is bound by 3 different curves. The curve over here would be the curve x equals 0. The curve over here would be the curve y equals 0. And this line right here, well, let's see, it's a line of slope -1 with a y-intercept of +9. So this would be a constraint region. Now notice 2 things about the constraint region. First off, it's bounded. It doesn't go running off to infinity. It fits inside of a breadbox. Also notice that this function right here, being a polynomial, is continuous on it. So the extreme value theorem says that both a maximum and a minimum exist. Now, they could occur at one of 3 places. They might occur inside the region. Now the inside candidates occur where the gradient of the function is equal to 0, or as undefined. Well, let's work out the gradient of f quickly. The gradient of f here is going to be 2 minus 2x, comma, 2 minus 2y. So if we set each of the components equal to 0, and so we get exactly one candidate inside the region. We get the point 1, 1. Next, we need to look along the constraint curves. Now there's 3 separate curves to look at, which means we're going to have to do 3 separate Lagrange multipliers. So let's first call this one curve number 1, C1 right here. So this first curve has the constraint equation x is equal to 0. And so this is going to be our first G1. If we were to work out what the gradient of this first constraint curve is, the gradient is just going to be 1, 0. And so the Lagrange multiplier problems of gradient of f equals lambda times the gradient of G1 and G1 equals 0 are going to become, so if we solve these equations, we get a point out of this, the point 0, 1. So the point 0, 1 is right here. That's the only point on this first constraint where we could possibly have an extremum. Now let's look at the second constraint curve, y equals 0. we could call this the function g2. And so the gradient of g2 will be, well, the derivative with respect to x is 0, the derivative with respect to y is 1. And so if we set up our Lagrange multiplier equations of gradient f equals the gradient of g2 times a lambda, and then g2 is equal to 0, we have the point 1, 0. This point right there. That's the only point on the second constraint where we could have an extremum. Finally, we have a third constraint curve here. The third constraint curve is y equals negative x plus 9, or equivalently, x plus y is equal to 9. Since this is of the form variables equal a number, we can call this the function g3. And so the gradient of g3 will be the vector 1, 1. So setting up our Lagrange multipliers, we find a point at 9 halves, 9 halves. And so that would be this point right here. Finally, we need to look at the intersection points, the points where the curves match up. So there's the point 0, 0, the point 9, 0, and the point 0, 9. So this gives us a grand total of 1, 2, 3, 4, 5, 6, 7 points to test. So let's write down our list. We have the point 1, 1, which we found by looking inside the region. We have the points 0, 1, 1, 0, and 9.5, or 4.5, 4.5, which we found by looking on the boundary curves. And then we have the points 0, 0, 9, 0, and 0, 9, which we found by looking at the corners. So what we'll do is we'll now apply f to all of these things, and we'll see what we get. So for example, f of 1, 1 is going to be 2 plus 2 plus 2 minus 1 minus 1. That's 6 minus 2, or 4. Similarly, these are the corresponding output values. Now notice that of all of these output values, 4 is the largest. And so that means that this is now the maximum value on the constrained region. On the other hand, of our negative values, negative 61 is the smallest, and so this will be our constrained minimum. Notice that this particular minimum is actually attained at 2 different points. Well, that's fine. We're just guaranteed one minimum value. It just might happen at more than 1 points. And so our answer is a maximum value of 4 at the point 1, 1, and a minimum value of negative 61 at the points 0, 9, and 9, 0.